Welcome to this explainer. If you've ever had a medical scan, you know the drill, right? You might be familiar with swallowing chalky barium or getting injected with some bizarre alien chemicals. Well, today we're decoding incredibly cutting-edge research that's directly shaping the future of medical imaging to change exactly that. We're looking at a massive, fascinating shift away from heavy metals and looking inward to a native hero already inside us. I'm literally thrilled to guide you through this because the chemistry and nanotechnology we're going to explore today are honestly nothing short of brilliant. Let's get into it.
So, have you ever actually wondered how an MRI sees inside you? We tend to think of MRI machines as these magical, giant magnets that just snap a photograph of our insides. But the reality? It's way more complex. A lot of times, the scanner alone just isn't enough to distinguish between, say, healthy tissue and a dangerous tumor. To get that absolutely critical, life-saving clarity, we need biological highlighters. In the medical world, we call these contrast agents.
Okay, let's dive into this explainer. Here's our roadmap for today. 1. The secret to clear MRIs. 2. The gadolinium problem. 3. Iron, a native hero. 4. Building nanotech vehicles. And finally, 5. The future of imaging. Section 1. The secret to clear MRIs. At a very basic level, MRIs work by interacting with the protons in your body's water molecules. Now, to make certain tissues really pop, doctors inject those biological highlighters we just talked about. These agents basically fall into two main buckets. Think of T1 agents as the tools that shorten longitudinal relaxation, essentially making water protons act in a way that creates a bright, glowing image. It's a positive contrast. T2 agents do the exact opposite. They shorten transversal relaxation to create a dark, negative contrast. Now, for the absolute sharpest, most easily readable diagnostic images of your soft tissues, those bright T1 agents, they're generally the go-to tools. Moving to Section 2, the gadolinium problem. For decades, the undisputed king of T1 contrast has been a heavy metal called gadolinium. And hey, to be fair, it works incredibly well. It boasts super high contrast efficacy and gives us that stable T1 brightening that lights up MRI scans beautifully. But it comes with some serious baggage. Gadolinium is highly toxic on its own. Because of that, it literally has to be wrapped in these chemical cages called chelates before it ever enters your bloodstream. The problem here, if those cages break down, especially in patients who already have impaired kidneys, it can lead to a really severe, sometimes fatal condition called nephrogenic systemic fibrosis. On top of all that, recent studies have shown that tiny amounts of gadolinium can actually be retained in brain tissue after multiple scans. Now, the clinical implications of that retention are still being studied, sure, but honestly, it's enough to have the medical community urgently scrambling for a safer alternative. Which brings us to Section 3, iron, a native hero. 3 to 4 grams. That is the amount of iron naturally existing in a normal adult human body right now as we speak. It's in your red blood cells, your liver, your bone marrow. Unlike gadolinium, which is a completely alien element to human biology, our bodies have evolved over millions of years to safely process, transport, and store iron. So think about it. If an iron-based contrast agent breaks down a little bit in the body, it's not some alien invasion. The body simply adds it to its natural iron reserves. This gives it an absolutely incredible biocompatibility profile compared to the old guard. But of course, there's a catch, and it has to do with its magnetic power. To be a great contrast agent, a metal needs a really strong magnetic moment. If we look at the numbers, gadolinium sits at a massive 7.9 magnetic moment, while iron I3 only has 5.9. Looking at that, you'd probably think iron is way too weak to compete. But iron has a secret weapon, its size. Because iron's ionic radius, at 0.64 angstroms, is significantly smaller than gadolinium's 1.00, the surrounding water molecules can get much, much closer to the iron. We're talking a distance of 2.6 to 2.7 angstroms compared to roughly 3.0 for gadolinium. And in physics, magnetic influence increases exponentially the closer you get. So that shorter distance acts as a massive equalizer in this underdog story. It completely counterbalances iron's lower magnetic moment, making it mathematically capable of producing a beautifully bright MRI image. Section 4. Building nanotech vehicles. Now here is the main obstacle we have to tackle. Even though iron is completely natural, free iron ions floating unattached in your bloodstream are highly toxic. They trigger this rapid chemical cascade called the Finton reaction. This reaction produces dangerous free radicals that can literally tear apart cellular structures. So, just like with gadolinium, we absolutely cannot inject raw iron. No way.
It requires a microscopic cargo ship to tightly hold onto the magnetic payload, safely and gently ferrying it through the delicate environments of the human body. And this brilliantly illustrates exactly how we build those cargo ships. In nature, microorganisms use special low molecular weight chelating agents to grab onto iron, and scientists are mimicking this exact behavior. Take a look at molecules like dopamine and tannic acid. Those chemical groups act like biological molecular claws that perfectly lock onto the iron 3 ions. They tightly coordinate the iron so it doesn't trigger any of those toxic reactions. But crucially, they still allow the necessary water molecules to get close enough to be magnetized. But those simple molecular claws are really just the beginning. Scientists take those claws and attach them to amphibophilic tri-block copolymers. Amphibophilic just means one part of the polymer loves water and the other part completely hates it. Because of this, they spontaneously self-assemble in water. It's like magic. They fold themselves into these incredible microscopic vehicles, forming spherical and cylindrical micellar nanoparticles. Now, these aren't just protective shells. They pack a massive density of iron inside them. In fact, testing shows that these specific nanoparticles actually outperform established gadolinium chelates at certain magnetic field strengths. They create a beautifully bright image, completely bypassing the heavy metal toxicity risk. It's a real game changer. Section 5, the future of imaging. Now, what's really interesting about this slide is that we're looking at actual in vivo PET/MRI scans of a tumor-bearing mouse. Take a look at the middle row. That's a T1-weighted anatomical MRI. Notice that brightly colored, glowing area overlaid directly on the gray tissue? That brilliant bright spot is the iron-loaded nanostructure successfully accumulating right inside the tumor, providing massive T1 contrast. This data is absolutely crucial because it proves definitively that these iron-doped vehicles can compete directly with gadolinium in living, breathing biology. They circulate safely, they find their target, and they light it up. Okay, let's distill all this complex medical chemistry down into a few core, easy-to-remember takeaways. First up, the industry standard gadolinium. It's effective, yes, but it carries long-term tissue retention and toxicity risks that we really can no longer ignore. Second, iron 3 offers a highly biocompatible, native alternative. Our bodies already know exactly how to handle it. Third, to actually utilize that iron safely, scientists have designed these incredible nanoparticles that act as armor to securely transport the iron through the bloodstream. And finally, these iron-doped micelles and polymers show excellent T1 contrast efficacy, proving they can absolutely compete with the old heavy metals. So, what does this all mean? Well, it leaves us with a really fascinating question to close out this explainer. If we can use clever nanotechnology to take a completely native, everyday element like iron and give it a high-tech upgrade into an advanced diagnostic tool, what other familiar native elements inside our bodies are just waiting to revolutionize the future of medicine? The solutions to our biggest medical challenges might not be alien chemicals, after all. They might literally just be the building blocks we're already made of, reimagined through the lens of nanomedicine. Thanks so much for joining me on this deep dive. I'll see you next time.